Hi, this is lab number 2, lines of charge. In this lab, we replicated the creation of charge tapes from lab number 1, but we applied more advanced computational models to more accurately calculate the electric force and electric field of a line charge and the total magnitude of charge on that line charge in equilibrium. From lab number 1, we concluded that the tape was positively charged with a magnitude of Q equals 1.4 times 10 to the negative 8th coulombs, and that was when we modeled it as a single point charge. Some important physics principles here are, again, Coulomb's law that tells us how charged objects interact with each other. The electric field of a point charge, that's what we used from lab number 1 to calculate the magnitude of the charge. The electric field of charge Q on an evenly distributed rod of length L, that's the model we're going to use here to see how that compares to the point charge formula in this case. The electric force and the momentum principle, which states that in equilibrium, the net force on an object is 0. And again, an understanding of force diagrams and the superposition of electric fields is important. So from lab number 1, we were able to conclude that the tape was positively charged, and we were then able to find the magnitude of charge on the tape by calculating the force of gravity on the upper tape, and then using the momentum principle to find the electric force on the tape coming from the lower tape. But this time, we're going to use the formula for the electric force of a line charge to find the tape's charge magnitude. And to do this, we're going to need to use our measurements from lab number 1, including mass, length of the tape, and the distance between the tapes. So when we model it as a line charge, and again set the net force equal to 0, we can set the magnitudes of the gravitational force and the electric force equal and solve for Q. And using those measurements of mass, length of the tape, and distance between them, we can conclude that the excess charge on the tape when modeled as a line charge of evenly distributed charge is 2.612 times 10 to the negative 8th coulombs. So another method to do this is dividing the charge tape into n equivalent pieces of tape along the x-axis, modeled each as point charges. And so each of those point charges would carry the total charge Q over n and be spaced out to cover the length of that tape. And so each of those point charges will also have a different relative position vector r based on their position on the x-axis. And you can sum up the electric force of each of these to obtain the net electric force of the tape. And so we can create a computational model that will show this in a visual form, and we have to first create an electric field and then create line charges by inputting locations and choosing a value for n, the number of point charges along that line, and then creating objects for the pieces of tape and finding the force vectors for gravity and the electric force. And here's the output. We've got the orange line at the top is the top tape, and the purple at the bottom is the bottom tape. Each of those is divided into 10 segments. And the green arrows in the top one are the electric force on each of those point charges. And then you can see that the x components cancel out. So that white arrow is the net electric force on the top tape, and the yellow is the gravitational force. And so when you change the value of the magnitude of the charge on the tape, to make the electric force and the gravitational force equal, you end up with Q is roughly 1.5 times 10 to the negative 8th coulombs. And so again, our assumptions would be that our measurements were accurate here, even though it might be hard to get a true accurate measurement, just given the setting of this lab. And then no other relevant forces were present, including air resistance and other charged objects. And we also have to assume that the charge is evenly distributed over the tape in order to model it as a line charge, and that the charges on the tapes are equal. And so when you want to compare the output of each of the models, so the least accurate one is modeling it as a point charge. That's what we did from lab number 1. And you can see that it's somewhat close. It's in the same magnitude as the most accurate model, but it's the furthest off from that. And then in between is modeling the tape as n finite point charges. So essentially the tape as a line charge is when n approaches infinity. So the more point charges you're using for n, then the more accurate that model will be. But the most accurate model is tape as a line charge because it is a line with the charge spread over it.